Can you see the screen being shared? Kindly confirm.
Yes, sir.
Okay. Um, so we are in week 5. Week 5 mostly deals with an introduction to Markov chains.
Yes, sir.
So yeah, do you have any specific questions?
No, sir.
Okay, so let's look at some sample problems. Um, I hope you're aware with the definition of Markov chains, right?
A little bit, sir.
Okay, I mean, did you get a chance to go through the lecture videos of week 5 that has the definitions? Um,
So actually,
if you want,
week 5.
uh, yeah, sorry.
Actually, I haven't visited the no lecture videos, but I have read little bit about lecture slides.
Uh, okay, okay. Okay, so I can recall the definition of Markov chains if you want to. Otherwise, we can just straight away look at the problems. How do you like me to, to take it?
Yes, sir. So please give an introduction, please, sir, of Markov chain.
Okay. Okay. So we are dealing with like discrete time steps, discrete Markov chains, which means that the Markov chain is an example of a stochastic process. So a stochastic process is essentially a process where um, for at each time step there is a random variable. So it's a random variable which evolves with time. Just give me a second. Yeah, so a Markov chain essentially is a stochastic process where you have a random variable which evolves with time. So recall what a random variable is. So essentially, what is a stochastic process? So a stochastic process is a time dependent random variable. Okay, so a random variable is a function. So if you have a probability space, so let's say this is a probability space, which is essentially a measure space. Um, there's a sigma algebra associated and there is a measure. Uh, where this is equal to 1. So a random variable is essentially a measurable map from the space to R. Okay. Now, a stochastic process is one in which this random variable evolves with time. So formally, you can think of a stochastic process as a map from this cross R. So this R is basically a time parameter. Uh, so often we write xt as uh, basically, so xt uh, is basically x of comma t. Okay, so xt uh, uh, is just the restriction of x to the time instant t. So this is the time parameter. So this is a stochastic process. In general, this is how it's defined. Now, a Markov chain is a special example of a stochastic process, which has a memoryless property. Now, Markov chains now this time parameter uh, can be uh, can be a discrete value time parameter, or it can be a continuous value time parameter. I think in this course they have restricted it to entirely discrete valued Markov chains. So a discrete valued Markov chain, um, so discrete time Markov process is, again, it's a sequence. It's a map, so you can think of it as a measurable map from this space. But instead of R was previously representing the time parameter. Now you have discrete time steps, so you can just think of it as like uh, as Z greater than equal to 0 to R. Okay, so this is your time parameter. And so essentially what this means is that for each time instant, for like for t equals 0, 1, etc., so on, you have a sequence of random variables. Uh, so let's denote these random variables as x1, x2, and so on. These random variables uh, have a particular property, which is the Markovian or memoryless property. So assume that, so before stating the general definition, let's state a more restricted definition. So assume that each xt takes values in a set S, where S is discrete. So S is a finite set. uh, so S is all the set of states. Okay, so S is a finite set. So assume that the elements of the set of this set S is the numbers 1, 2, 3 up to, let's say, some k. So we say that a sequence of random variables is a discrete time Markov process with a state space S if the probability of xt equal to I, given that x0 is equal to I0 and x t minus 1 equals I t minus 1, where each uh, I and I0 up to I t minus 1 are elements of this state space S, is equal to probability of xt equals I, given that x0 equals I0. Okay, sorry, given that, I'm sorry, xt equals I, given that xt minus 1 is equal to I t minus 1. So it is independent of uh, uh, what the other random variables. So essentially it is only dependent. So the value of the process at the time instant t is dependent uh, on what value it took
Oh,
in just the previous time step. Yes. Did you have a question?
no, sir, no, sir.
Okay. Um, Furthermore, if this if for so essentially if this probability of xt equals I, given that xt minus 1 equals j. So if this is independent of time, is independent of t, then we call it a homogeneous Markov chain. Okay. Now, give me a second. Okay. So with this introduction, let's look at some of the problems. So most of the problems we will be dealing with will be with respect to homogeneous Markov chains. So then for I comma j, uh, for I comma j, which belongs to essentially if you take some I comma j that belongs to S, you can form a matrix M where Mij, so M is basically a matrix whose dimensions is this. So mod S is the number of elements in the state space. So M is a matrix of size S cross S. And each entry of the matrix Mij um, is basically the probability of xt equals I given xt minus 1 equals j. Okay, so you can actually form, you can have a matrix like this. So this matrix M is called the transition matrix. Okay, so let's look at some of the problems. related to this. Um, so one quick thing is we can see one quick thing as follows. So if we want to compute this probability, so if we want to compute the probability of xt being I, well, that's equal to the sum over a probability of xt equals I, xt minus 1 equals j times the probability xt minus 1 equals j, and you take the sum over of all j belonging to S, right? So this is equal to mij by how we've defined the transition matrix. And uh, along with this term, and you have summed it over all j. So if you can form a column vector uh, pt. So let pt be a column vector where so pt is a column vector where each entry of pt, so pt of I is equal to probability of xt equals I. Okay. So essentially what I'm doing is I'm taking these probabilities, probability of xt being I, and I'm forming a column vector. So then this expression basically tells us that pt is equal to m times pt minus 1. Okay. So if you notice carefully, uh, you can write this thing as equal to, so essentially if m uh, if mi is the ith row of m, this expression is basically the inner product of mi uh, times pt minus 1. Okay, so so what we basically get is that pt of I is equal to this, the inner product of mi times p t minus 1. And you have um, right, and you have these inner products. Uh, so you get pt equals m times pt minus 1. Okay. So now this is a recursive relation. So in particular, you get pt equals m to the power t times p0. So this p0 is the initial probability of the states. Probability distribution over states. So it is basically, so essentially p0 is a probability that uh, so p0 comma I is the probability that x0 equals 1. Okay. So sometimes in the literature, instead of this matrix M, we consider the transpose of this matrix. So sometimes Yeah, sometimes we consider the transpose of this matrix. So let's, instead of calling it as PT, let's call it as Pn. Pn equals m to the power n times p0. Sometimes we consider the transpose of this matrix P. So essentially, that's in that notation. So considering transpose of M. So in that notation, we have Pn transpose is equal to P0 transpose times M. Okay. So okay, let's just write it as M transpose. Sometimes this is also called the transition matrix. Okay, so it depends on the notation. So with this, I think we can solve most problems. So let's look at the first two problems. Are you with me? Do you have any
Yes,
questions?
sir.
Okay,
No, sir.
okay, great. Um, so the first two questions are, so we have a Markov chain. The first problem is we have a Markov chain, x0, x1, x2, x3, and so on. So now what we do is that we take only the even terms. We take x0, x2, x4, and so on. In the second problem, we again have the Markov chain x1, x2, x3, so on. We take only the prime terms of that Markov chain. Okay. So the question is, in both these cases, can we say that these are also Markov chains? Did you were you able to get the question?
Yes, sir.
Yeah. Can we say that these are also Markov chains? Well, the answer is yes. In fact, if we have any such Markov chain, um, so let me just give a small result. Uh, Fact, if x1, x2, and so x3 is a Markov chain, then any subsequence in a subsequence is also a Markov chain. Okay. So why? So let's say we have some subsequence, um, K1, K2, so on, and we have another Markov chain where y1 is equal to xk1, uh, y yn is equal to xkn. So then y1, yn, so on is also a Markov chain. Uh, and why is that true? So notice that so the condition for a sequence of random variables to be a Markov chain is basically that it has this memorylessness property, that it is only dependent uh, on the previous time step and not the time steps before. Um,
Yes, sir.
so that's what we have to show. The probability of yn equals k, given, or let's say probability of yn equals uh, in, given that y equals I1, yn minus 1 equals in minus 1 is equal to probability of yn equals in, given that yn minus 1 equals in minus 1. This is what we have to show. Now, if we just substitute what we've just defined, then probability of yn equals in, just substituting back. This is equal to probability of x kn equals in, given that x k1 equals I1, x kn minus 1 equals. Okay. So here basically you have k1 is smaller than k2, smaller than k. Now, so you have to iteratively write this as as a sum of conditional probabilities as follows. Um, okay, so let's consider this a random variable, or right. So let's consider this joint random variable. Okay. So the joint random variable is, or let's consider the joint distribution of probability of x kn, x kn minus 1. Sorry, I should write it as probability of x kn minus 1. It's not n minus 1, but kn minus 1 up to x. So let's put kn minus kn minus 1 equals a. So this is equal to probability of x kn minus a plus 1, given that x kn minus 1 equals in minus 1 dot 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 up to probability of x k minus 1 equals I. Okay. So I think it's becoming a bit cluttered. So let me write it clearly. Consider the joint distribution. xkn minus 1 up to xkn minus a plus 1, given that xk1 equals I1, xkn minus 1 equals in minus 1, where a equals kn minus kn. Okay. So let's consider this probability, this joint distribution. Um, so notice that this joint distribution uh, is dependent only on this term. It's independent of the rest of the terms, right? I hope it's clear why this joint distribution is dependent only on this term, right? It's independent of all the terms before it. So
Yeah.
probability of this term uh, is essentially this whole thing is equal to x k n minus 1 equals I n minus 1. Because this is a That's because this is a Markov chain, right? So xkn minus 1,
Yes, sir.
xkn minus a plus 1, this is a Markov chain. And because it's a Markov chain, so you can then show that this joint distribution is independent of the terms before it. So it's only xkn minus 1 equals I minus 1. So then the probability of xkn equals in given xkn minus 1 equals in minus 1 is is just uh, is just a marginalization of this distribution, right? So this is just equal to um, sum over of um, let's see, probability of x k n equals in comma x k n minus 1, sorry, x k n minus 1 equals some j1 dot up to x k n minus a plus 1 equals some j a minus 1 given x k n minus 1 equals I n minus 1, where this j1 to j a minus 1 varies over s cross s up to a minus 1 times. Okay, so this is just a marginalization that we're doing. Uh, where we are marginalizing over all the intermediate random variables from x kn minus 1 to xkn. So the intermediate steps we are marginalizing over that. Right. So right. Now each of these terms, probability of xkn equals in x k n minus 1 equals j1 up to x k n minus a plus 1 equals j a minus 1, given x k n minus 1 n minus 1. Well, you can just write it as um, by repeatedly applying conditional probability. Uh, this is equal to probability of x k n equals I n given x k n minus 1 equals j1 times uh, times basically probability of x k n minus 1 equals j. Yeah, so you can get you can understand how we are getting this thing. So in a more compact notation, we can write this as equal to this product of probability of x k n minus r equals j r, given that x k n minus r minus 1 equals j r plus 1. Okay, where r varies from 1 to a minus 1 and j a equals I n minus 1. Okay. So this is the way you obtain the probability, and it's clear that uh, so the reason why uh, xkn we arrived at this was because uh, so this sequence xkn equals in up to all these terms is so essentially from here we can get here because the probabilities at each of these steps is independent of what happens before kn minus 1. Okay, so the crux of the proof is, so let's write it down. Crux of the proof. So the crux of the proof is this observation that um, that probability of x kn equals in x kn minus 1 equals j1 x kn minus a plus 1 equals j a minus 1, given that x kn minus 1 equals in minus 1. xkn, yeah, xk1 equals I k1. So this is equal to uh, probability of this given xkn minus 1 equals I minus 1. So this follows from the Markovian property of the original Markov sequence x1. Okay. Um, yeah, so any subsequence of a Markov chain will also be a Markov chain. Uh, as a result, in both of these examples, um, They are both Markov chains. Now, can you tell if they are homogeneous Markov chains?
For homogeneous.
Yeah, are they homogeneous Markov chains? Both in both the cases 1 and 2. Is this a homogeneous Markov chain? Is this a homogeneous Markov chain?
Yes.
You can assume that the original Markov chain is a homogeneous Markov chain. So if this is a homogeneous Markov chain as well as this is, then what can you say about these subsequences? Are they also going to be homogeneous?
Uh, yes, sir. I think that then that will be also homogeneous Markov chain.
The first one will be homogeneous. The second one will not be homogeneous. Because recall what the definition of homogeneity. Homogeneity means that uh, the probability, so the probability of yn uh, equals some I given yn minus 1 equals j. So this is independent of n, is independent of n. It's independent of time. Time here is n. So it has to be independent of n. Okay. Now for the first case, x0, x2, x4, it is actually independent of n. It is independent of n because you have because the subsequence that you are choosing. So essentially, you're choosing all the even numbers. So you have 0, 2, 4, and so on. So the subsequence that you are choosing, uh, there is a regularity in that subsequence, and which is why the probability is actually independent of n, and you can actually estimate the probability. So the transition. So if we want to compute this transition, so if you want to know what is probability of yn equals I given yn minus 1 equals j. So if you follow this derivation, uh, right. So if you follow this derivation, um, so then what does it come out to be equal to? Well, the probability yeah. So the probability comes out to be equal to this term, right?
Yes, sir.
Yeah. So here, so in the first case, you have all the even numbers. So what are the successive terms? So yn is x2n, yn minus 1 is x2n minus 2, right? So if you want to marginalize, you are marginalizing essentially over this random variable, which is x2n minus 1. Right, we are marginalizing the distribution of this. So the probability of x to n equals I given x to n minus 2 equals j is basically equal to sum over of probability of x2n equals I, x2n minus 1 equals k, given that x2n minus 2 equals j. And we're marginalizing this over all k, right? So, okay, so if we just split it down, if we just proceed further, this is equal to sum over of all k down to s, probability of x2n equals I, given x2n minus 1 equals k, times the probability x2n minus 1 equals k, given x2n minus 2 equals j, right? Um, so this is so this entire expression is independent of n. It doesn't matter what n you choose, it is independent of n because this term is independent of n. Well, what is this term? This term is equal to mik, and this term is equal to mkj. So it's mik times mkj. Right. And here you're doing sum over of that. Whereas in the later case, where you have uh, a subsequence which is not regular in the sense that the differences between the indices is not constant, um, you will not have a homogeneous Markov chain because you can show that uh, the transition map is going to be dependent on n. So essentially, so let's just take a simple example. So let's say you have 5, 7, 11, 13, um, 17, 19, so on. So let's take an example between 11 and 13. You have to marginalize with respect to this random variable x12. But from x13 to x17, you need to marginalize over random variables x14, x15, x16. So naturally, the transition map from 13 to 17 and the transition from 11 to 13 is not going to be the same. So it's going to depend on the index. Okay. And therefore, it's not going to be a homogeneous Markov process, Markov chain. I hope it's clear, right?
Yes, sir.
Okay, let's move on to a different problem. Okay, so there is a transition matrix of this random variable which is given to us. Um, Yeah, so given this transition matrix of the Markov chain, so notice that we showed before that we have this that Pn transpose is equal to P0 transpose times m to the power n. So this is a relation between the probability of the states, the distribution which is induced over the states. Um, Along with the initial probability, with respect to the initial probability. Here M is given as this matrix, and here we want N equals 2021. So if you do a simple calculation, I think you can show that M power 3 is the identity matrix. Okay. So M power 2021 is equal to M power 2019 times M squared. Now this is identity and this is M squared. Okay. Um, yeah, now it's just simply substituting this formula. So it's half. So it's half 1/4, 1/4 times M squared. And this comes out to be equal to, yeah, this comes out to be equal to 1/4, 1/4 half. It's just plain substituting.
Yes, sir.
Yeah. Um, Okay, let's look at one more problem and then we can wrap it up. Right. So right. So a simple example of how to read the transition matrix and solve problems based on that. So you need to compute. Uh, you have this Markov chain. The transition map between the states is given, and you need to show. Need to compute this essentially. Uh, so the simple way to read the transition map is basically as follows. Uh, you are at state x equals to 1, you are in 3, and then from 3 you go to 2, and from 2 you go to 1. Okay, so the so you so this is equal to probability of x1 equals 3 times the transition probability from 3 to 2 and then from 2 to 1. Okay, so that is equal to m32 times m21. Okay, so probability of x1 equals 3 is equal to half because x1 equals 1 and x1 equals 2 is both 1 by 4. So this is equal to half. M32 is given to us. M32 is half. And M21 is 1 by 3. So the correct answer is 1 by 12.
1 by 12. Okay.
All right. Do you have any questions? Then we can discuss them. Otherwise, I'll wrap it up here.
No, sir.
Okay. Okay. Great. Okay. Thank you for joining.
Thank you, sir.